Well, thank you for staying here. It's the last talk of the day, right? So I appreciate you guys are here. I'll try to do entertaining and insightful, so you appreciate this. First of all, I want to kick it off by asking you a question. If you had to put in a suitcase something that could truly define you, what would you put there? Well, would you put a t-shirt, a ratty t-shirt? Would you put your favorite albums? Would you put a painting? What would you put? I mean, keep that in the back of your mind. We'll come to that later. And yeah, time series forecasting. So this is the name of the talk. I'll be focusing on the data science bits on it, so a bit more in Apache Spark, obviously, because we want to submit, than in ElasticSearch. I work at Adyen. I don't know if you guys know Adyen. Possibly if you're Dutch, you know. Otherwise, it's a great opportunity. Adyen is a payments processor. It's a tech company. It's a Dutch unicorn as well. We are worldwide. We process payments worldwide. And we also get a lot of cool data. And we try to do, as a tech company, cool things with that data. One of the things that we try to do is to monitor the volumes of our customers. We call them merchants because, of course, they are businesses that we capture the money from them, from you, and we give it to them, right? So for us, it's important to offer this service to them, so we know that everything is all the time. We know what's happening, right? So monitoring is really at the core of the platform builder. So if you want to monitor the volumes of your merchants, sounds easy, right? You see all these payments going through, so you know I should be seeing that. It is until you try to actually solve it. So the first attempt was actually, having the right problem and using the wrong technology. So basically, you basically have a SQL query that could try to estimate a mean, which is actually a fantastic operator if you don't know what to do, and then, have some sigmas up and down and then fire an alarm. The problem with that is that you're not harnessing the performance of the algorithm, and indeed, the result of that was that we were flooding our poor colleagues of support duty with loads of false positives. These guys couldn't absorb this load, so we needed to take measures. And this, what we did is trim it down. Let's choose a bit which are the merchants. Let's choose, that we can predict better, that are maybe bigger in volume, so they are more predictable. But that's quite not how we are, because we have a thing called the formula. It's basically the DNA of the company. We try to really benefit all of our merchants, not just one. So we needed to don't think about that. We just kind of just leave it there, right? So we try to put requirements on how we should invent a smarter system to solve this problem. Right, so the first thing you can do, of course, is reduce the number of false positives, right? So this is a reference to Rick and Morty. If you guys haven't seen it, you should do it. So false positives, you want them down. But still, of course, that's a well-known problem in classification. You want to catch the bad guys, right? So all these true positives, you want them to be able to catch them, right? On top of that, we have an ever-growing pool of merchants, and we want to grow, and we grow with them. So we need to do that at scale. So for us, we need to come up with a solution that's not going to be, at some point, bottlenecked by technology. Also in data science, it's quite important to benchmark, to know what you're doing. So we also want to have a solution that allows us to, at any point in time, benchmark, know exactly how we're doing, and then maybe roll it out or not. And lately, so the last requirement would be to connect to the live platform. Now, the core of the business of Adyen, of course, is processing payments. So the live platform is a very robust, fast thing. And to connect to this thing is not obvious. There's a lot of requirements, security requirements, latency requirements, and whatnots. And you try to build a solution that comes from machine learning into this thing, it's tricky, right? Anyway, we're motivated, we'll get it done somehow. And yeah, so how can we solve this? Not so fast. First of all, what is really an anomaly? I mean, I was asking around, I said, okay, what is really an anomaly for guys? So any person has a different concept of what an anomaly is. Some people would say it's a complete drop in volume. Some other people would say just a fluctuation. Another guys would say a significant drop. It's not really captured. It's not really known what it is an anomaly. And that also means that we don't have a labeled data set where we can learn from and say, oh, that's an anomaly. So we can infer that behavior and then spot it later on. Then we are attacking the problem of time series. So I don't know if you guys have worked with time series forecasting. I've done it. It's not as fast as doing forecast equal true like this morning. It's, there's a bit of science behind that. And you need to do that at scale, which is kind of like small data, but at scale. It's complex. And then again, connecting to a live platform and deploying models. Now, we do have MLflow-based solution now at home, but back in the day, we didn't have it, and we just couldn't wait. So, okay, these are problems. These are the technological problems, but then you also have like the user problems. And people they all the time talk about big data here, big data there, and they mean, oh, I have a Hadoop or I have Spark. But from the user point of view, big data also have some other consequences. So the first of them is that you need to use big technology, right? So, okay, we're in a Spark Summit, that's kind of a problem solved. We have Spark at home, we can do that. Then you have a problem of diversity. So we have a lot of merchants. They're all of them different, and you still want to have like a model or a bunch of models to rule them all. You need to look at a lot of different cases, right? And the third one is the one I like the most, is the big consequences, I call. So imagine this scenario. So you have 1,000 merchants, and we have more than that. And you try to evaluate every 10 minutes whether there's an anomaly or not. And you have a model that is 95% accurate. That means that you'll be raising north of 50,000 emails to your support team, which is clearly not acceptable for a tech company. You need to do better there. You're not going to reduce the number of customers, obviously. You want to be faster than 10 minutes, and you want to get faster. So the only choice is actually to improve on the accuracy, right? So let's look at the big picture of the whole solution. How can we do this? So here we are. I don't know if you guys attended the previous talk about Adyen on the big data platform we have. So basically you have Adyen, and here by Adyen I mean like the payments processor, throwing volumes to, a data stream to our big data platform. Then this big data platform doing more things, and then throwing predictions back. So you can tell whether something's wrong or not. Which technologies are actually behind the hood here? So you can guess. We have a big data platform that's based on Spark. And then we are using ElasticSearch, which I'm not an expert, but I'm a user, and we're using it as a hot storage. So we can really get the volumes very fast from any merchant with any aggregations and so on. Cool. Now, how do we solve the time series problem? So we have this platform, we have to use this. Let's look at what's in the market, or what can we use in sort of time series, right? It's a well-known problem. There's a lot of research. A lot of people have actually invested their time trying to solve it. Well, this is a bit of the ecosystem that we have seen. So Databricks and 2 Sigma have this Flint project going on. So you see these two names, and you're like, nice, I'll use it. OK. There's an old repo on GitHub called SparkTS. Actually, it was quite popular, but it's not popular anymore. And then you have Facebook Profits. I don't know if you guys have heard it, but I personally like it a lot. I think it's a very, very good approach to solving the forecasting problem. And also you have, well, if you're using Python, obviously you're using stats models and everything that goes with there, time series decomposition or EMA, whatever. You have it there. So still, there's something missing there. And then this is when you realize that actually when you're dealing with time series, you might be dealing with the big data, but not that much big data. Because if you have 1 year of data sampled at 1 minute, and you're using double 64 precision, that's 4.2 megabytes. Which is not big data, right? Fits my laptop perfectly fine. The problem is that I have tens of thousands of those, and I want to do that at the same time. That's when it comes to at scale problem. So we took a bold move there. Everyone's talking about deploying, serving models, and so on. But then we realized that what we could do instead is score in Java. This is bold. I mean, normally data science people, they go and they say, I live in Python. I love Python myself. So I live in Python. I train, I fit predict. Later on, I score, I come back. I don't really get into the insights of what's going on. I mean, I like to, but people usually don't. We also had this problem of not serving all of our merchants. And for us, it was like, we need to do something about it. So we need to launch fast and iterate. It's actually, again, in the formula I referred before. So OK, let's see. Let's try to just for once imagine to score in Java. What would it mean? It means we need to transport somehow the model. So we train on Spark. We have the Java platform. They need to talk, and it needs to happen right. It needs to be performing fast. So you don't want to be like solving like things in Java and then like adding latencies to the things. And that also forces you that, well, you can't really just train a model, fit, predict, live there, store it, and then I bring it back. No, you really need to get inside. You need to understand what you're doing. You need to harness the maths. This is hard. I mean, you really need to know the model behind. You need to recreate the scoring equations somewhere else, and the numbers need to match. Otherwise, you cannot do it, right? So let's see. It went from this picture, right? So we send the volumes in. The number crunching happens with Apache Spark. And instead of sending the predictions back, what we're going to do is send the model coefficients back. And then that would solve the problem of being fast, transporting things. But we need to come up with a model that is simple enough so that we don't just get very, very muddy in the Java side. Because I particularly don't enjoy doing maths in Java, but yeah. So we start researching, how can we do this? We can certainly use out-of-the-box solutions, at least to learn and understand how things happening, but we can't need to customize it. So we started with, as you do in data science, you start with a research stage. So we took, an overview of the different attempts to solve this kind of problems of anomaly detection in general, not just time series. Fourier components, it's one way of decompose your data by looking at the frequencies. ARIMA, very popular in the time series forecasting. Isolation forest, very used for anomaly detection, but mostly for multidimensional data. Autoencoders, I personally like them a lot, but I'm not very keen on having to kind of redo artificial nets, neural nets on Java myself. The same goes for the XJVM. So we did this, and then we came up with our own model based on everything what we learned and everything what we have seen. And the nice thing about it is that we can tailor it to our needs. So this is the model. And the maths are there because design put them there, but they are true. At the end of the day, what you want to do is you want to set the probability of an anomaly, say 99%, 99.7%, 3 sigma. And you want to make sure that what you're seeing is above or below that probability, right? If it's odd enough, then you raise an alarm. That's basically the idea, right? So how do you achieve this? Let's go step by step. The first thing the model will do is a pre-sampling step. And this is extremely important because we have a very diverse pool base of customers, of merchants, and not all of them are having the same number of payments per minute or per second, or some of them are stores, and they might see a customer from time to time. So this pre-sampling algorithm, what you could do, you could basically say, OK, I'm going to put this guy in a bucket of 10 minutes, and this guy in a bucket of 15 minutes, and this guy in a bucket of 5 minutes, because it's faster. There's more density, so I can estimate it faster. Then, if this works right, then I'm able to see a pattern that I can estimate, right? The nice thing about our data is that it's business cycle bound. What it means is that we are humans. Every day, we do things, but we're quite predictable. So we have a very strong seasonal component on it, and it's very important to track it well. So we decided to use Gaussian basis functions to be able to throw a number of functions of those, and then estimate those seasonality well. Another problem we're facing is that the volumes is not just like a flat, think of a flat sine signal. You have your seasonality, but volumes go up and down. I mean, account managers decide to turn off and down more volume or route it somewhere else, so you see fluctuations. It's very difficult to learn from that. So that's why we have a piecewise linear trend decomposition. Right? We don't impose a continuity condition just because of that, because it's super random when the volume can go up or down, and then we will still be able to break it down, though. A favorite from the forecasting is events. Black Friday, Christmas, sales increase. But might be other events that just are not that predictable. So we also can throw events to the model, and if the model rolls back long enough, can learn from it, or actually not learn from it is more accurate. You tie this all together with a simple model because you want that to score in Java. So what you do is just throw a rich regression. Super easy. Why? Because the scoring of a ridge regression is just a Cartesian product. So it's simple enough. We can do it in Java. And then I need to kind of estimate my confidence intervals. So how do I do that? Well, I just throw a quantized regression to these deltas, and I try to come up with some statistical sense out of it. So this is the complete model. Pre-sampling, Gaussian basic functions, linear trends, events, the ridge regression, and the residuals. And now I'm going to show you some plots, so you kind of digest a bit what I just said, right? So the first thing I will show you is the piecewise linear trend decomposition that we took the chance to name it trend spotting. So what you do here is you place, so the algorithm automatically finds hinges. And hinges is basically places where you have seen fluctuation in the trends, and you decide to say, OK, up until here, now it's a different thing. So you put a hinge, right? And in between the hinges, you have segments that you're going to estimate in a different way, like with different trends, right? That's the algorithm will take care of it. So we estimate the hinges there, so you can observe here how the different data, so the first two signals up and down, they are basically the same thing, and how it's been estimated on different trends. And then when we throw in the seasonal component and confidence intervaling, how does it look like? So this is, for example, an example of our time series. So what you see in the top plot, the red lines are real volumes, the blue lines are our estimations, and the top is the training set, 3 months of data, and on the bottom is the test set. So the algorithm has seen that data, predicted the blue line, and the red line is what realized. Now, that's really what I said. Our data is very seasonal because we're bound to business cycles. People go to work at the same hours. They take rides at the same day. They order food at the same time. So that's why, for us, the seasonal component is so important. Another example could be, damn, we missed an event. That's the thing with events. Events are very colorful. Like every country have different events. Event might just pop in because of there's a strike somewhere, so people are not taking trains anymore. It's very difficult to actually learn from there. So you miss them. You miss them. You're going to raise false positives at some point. That's an example, for example, of a store with a lot of volume. So you can see it's a store because at night it's not processing. And that day we missed it. We predicted something that actually didn't happen. And then at the bottom, what you see is another customer around the same area that does way less volume. But the pre-sampling put it in a different bucket. So you still see 1 point there for that guy, not many, the signal, and but still predicted positive, accurately a problem there. Well, it wasn't. It should have learned if you show the event, but we didn't. This is fine. I haven't spoken about Spark yet, and we are in Spark Summit. So how can you do that at scale? Right? So that is easy to solve in your laptop. I have my data, 4 megabytes, boom, 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 easy, super fast. Yeah, so we have 10 of thousands of those, or tens. These are a bit of the pillars of the Spark implementation. We want to be able to reuse that. And reusing, I mean, as data scientists, we play a lot on notebooks, and we want to be able to keep working on notebooks. And also, this notebook code should be able to be in production somehow. And maybe another, as it happened, another team might take this and use it for another purpose, right? Again, scalability, I just mentioned it, right? So you have all these different time series, and you want to do that at once, and you'll not be tangled in waiting. And another thing we also did is to cross-validate time series, which is also a bit more scientific, but we threw it in there as well. So first of all, reusability. So this is the implementation of our SeasonalEstimator. We basically reuse the scikit-learn interface, fit predict, and you learn a bunch of features, right? So in this case, for example, we threw in to learn, the hour of the day and the day of the week and some noise. And that's exactly what it predicted, because it's able to understand an hour of the day or the day of a week or the day of the month, things like that. Now, let's use Spark, really, because so far we haven't done it. So how we did it is like that. So Search, which is our data engineer, came up with the idea, said, let's kind of use a lot complex types. And I was very hesitant at the beginning, but I must say it works. So what you're going to do is, every day, you're going to collect a list for your merchant of the timestamps of the payments and the volumes of those payments. So we have a window function, say every minute, and then you aggregate that on a complex time. So you have a list per day, per merchant, of the payments that they have done. And when you this is happening every day in our ETL in the pipelines. Now, when we fire up a training, the first thing you do is collect all this into a list. So you have a list of a complex type that contains 2 arrays inside. So it gets complex, right? N's complex type. So, and then you mix it up with the hinges and the hyperparameters you came up with, and then you distribute a UDF. Because effectively, in one row, you have all the data you need. So you apply to that row a UDF, where you have SeasonalEstimator on it, and you come back with the numbers that you need, the coefficients and performance metrics. Let me start first in the cross-validation. Cross-validation of time series is not that simple. There's a few articles there, and actually we couldn't really reuse what comes out of scikit-learn. We had to come up with our own time series split. We name it time series week split. This is how we do the faults. I think it's very graphical, the way we do it. We need to keep consistency on how much train data, test data we are throwing to the faults. And we're also very keen on at least having 1 week on the test sets, because that's really like, for us, it's a business cycle, a week. And then the scoring, you cannot just throw in, say, arc square predictions. We came up with another, let's say, way of leveraging as well the sampling. So if I can predict a time series this accurate at 10 minutes, and I can predict this guy a bit better at 20 minutes, maybe I prefer to use the 10 minutes one because it's faster, even though I'm compromising a bit the accuracy of the prediction, right? Because it's good enough. So once we have done all this, we come up with the output, which is a data frame that contains, it's highlighted there somehow in yellow, a sampling group, a train results, the coefficients, the hyperparameters, and a cron rule. And the cron rule will drive when are we firing those monitors in the real-time environment, because it needs to be consistent with the sampling. I don't get deep into that. It's a bit of a thing you need to do to be able that you are scoring and sampling at the same time to keep consistency of the timestamps. So when you have done all this, you have trained all those thousands of merchants. You have what you do. I mean, you want to know that if the training went well, right? So this is a performance map, for example, of our customer base on one of the versions of our algorithm. So on the x-axis, you will see a metric of the volume. On the y-axis, you might see like the bottom is 0, R square prediction, and at the top is 100%. So what we're saying is that when we throw more data, so that when the merchant has more data, it's more predictable, obviously. But then it's like things can get better there. It's just the dots go down a bit and then up. So you roll out new versions, you keep training, you keep improving your model, and you come up with a better model, right? So now we're happy. We have all these guys, they're sticking on the top. This is where we want them. And actually, this artifact of the line is because of the buckets that we offer for sampling. Also allow us to do something is when you deploy a model, you don't possibly want to deploy, okay, that's the model, boom, this is live. You want to harness it. So we started a canary rollout. So you start from the top, which are the most predictable ones, and you go down to see if our support teams are actually happy with what is happening. You don't want to flood them already with alarms. There's a human component actually at using machine learning, right? Okay, so far I'm focusing on the performance of how well I am forecasting a time series, but I also want to, at the end of the day, it's a classification problem. Is it an anomaly or it's not an anomaly? I don't have a labeled data set, or do I? Because what we do is we estimate our recall by a training time, throwing random draws of outages, which are synthetic outages. And if we are able to recall them, if we're able to pick them up, then we have an estimate of our recall. We call that a synthetic recall. And then we can use the test set, the alarm rate of the test set, as a proxy for our precision. Because if we're not predicting well, we're going to be very noisy. So our alarm rate on the test set is going to be off the charts. Now, we don't want it to be a strict 0 because something may have happened. So we allow a bit of margin there, a bit of temperature there. So we have precision and recall, proxies at least for this. So we can throw this plot. Nice. So we see at the x-axis the alarm rate. So we want this to be at the left because it's 0. And on the y-axis, we have the recall that we estimated through the synthetic outages. And we nicely see all these guys sticking up at this sweet spot in the corner, which means that we can actually estimate them well. It's good, right? So this gives us confidence that we can roll these people out in production, and we're not going to create too much noise. We have proof. So we have to roll them out to production. How do we do this? So this is an example of the model payload. Now, come back to when I started the talk about the suitcase. This is what we put in the suitcase. We don't need the shielding. We don't need the capability to just call an API predict or whatever. It's just numbers. That's the DNA. That's the DNA we extract from the mosquito. We throw away the mosquito. So we just transport those numbers. And because the equations are simple enough, then we score them well in Java as well. Right, so all this sounds very good, right? I mean, we have a model, we have the numbers, we have the performance metrics, we have the Java side. Let's put it into production, right? So I was playing around, I was putting there, seeing does it work, I think it works, whatever. So the support, the platform operations guys and the supporting guys were like, hey, let's roll it out already. Yeah, let's do it. So we sat down and we're like, okay, now we go live. And we go live, and what happens? Nothing happens. So we go there, everyone's looking, and they look at me, it's like, hey. And I'm like, oh, wait. And then you realize, isn't that what's supposed to happen, actually? If you're monitoring well, and there's nothing bad going on, then you just don't raise alarms. This is exactly what's supposed to happen. So we went to the logs, and we saw if actually the monitors were firing. We saw the predictions, we saw the numbers, we saw the resolution. I don't need to raise an alarm. And it was happening. So we were very happy about that. But we also learned a lesson there. So you can just put a monitor there, and human people cannot really consume that. How do I know whether it's working, not working, or just not firing? How do I know this? So we built a Grafana dashboard. And this is a tool that is super useful for us. At any point in time, we can query for a merchant, for a shopper interaction, and it will give us the real volumes at different periods of time, the estimates, and whether an alarm was fired or not. And this is like a very good tool for a human to understand whether if the alarm was actually raised, was a legit alarm, or was just noise, an artifact of the algorithm. And let me go now through a bit of a few stories that we came up with through having this thing living in production. It's a bit of a quiz. So we saw this on the data, and this is a merchant of ours that it's a food delivery rider-based merchant in Taiwan. So what happened? So you see this. Obviously, the volumes are not according to the expectations. You're doing that with a lot of confidence, so you're like, I know that this should something off there. So we reached to them. So we have the support utility guys reaching to them. They came back to us. Duh, there's a typhoon actually here. So no wonder. Which makes me think, because this is not a flat zero. There's actually people riding when there's a typhoon there. So, okay. Then another example would be this one. A colleague of ours goes to Trento station in Amsterdam, sees this shop. It's a merchant of ours. The shop is closed for maintenance. They are repairing something. Goes back to the desk and says, would it work, really? I mean, it should have fired, right? Nicely, he shared even the nice message with us and said, like, yeah, it's working. So this is how much we care there about the merchants. We really want to monitor them and be able to pick up the bad stuff real quick. Actually, there's this anecdote that there was a meeting. I wasn't there, but there was a meeting, and we're trying to close a potential customer. And it was more like classical-oriented IT merchant. And they said, hey, listen, how's your call center? So when I call, how do I make sure that actually someone picks up? How many people do you have there? To which our colleague replied, you don't call us, we call you. Because we know before you that you're down. Yeah. So that's been it. It's been enough data science and data engineering for today, I guess. If you want to recap on something, there's a post on Medium coming up about this. exploring this information as well. And yeah, if you have any questions, I'll answer that. The easy ones, and the difficult ones, we take it offline. Yeah, so that's it. Thank you.
All right, we do have a few minutes for Q&A, so just raise your hand if you'd like to ask a question.
Yeah, thank you. It's really a good talk, and it reminds me of lots of questions.
All right.
And the first one is, so you are using the historical data to predict the next week's transaction volume. Yeah. So how this come to the anomaly detection, and what's the threshold you set to whether it is an anomaly or not?
Yeah, so when an operator, a support guy, can set a monitor, right? So we have our interface to set a monitor. What we offer is a probability. So through the quantile regression, we can tell in which is the probability you want to pick up an anomaly, right? Normally, you want to do that with a lot of confidence. So the lower the probability, the more events, the more alarms you're going to raise. So I think we have it set at 99.5 now, or something like this. So yeah, so you predict your data, you come up with your confidence interval that's given by the probability you're setting.
Yeah, but the prediction is the transaction pattern in the coming weeks.
Yeah, exactly.
How this convert to the classification whether it is anomaly or not?
Yeah, so the flow in real time, you are in Java, right? Yeah. So you know your coefficients, you throw a timestamp to it, so you know what's the volume you should be seeing, and then you have ElasticSearch, right? Hot storage, you get the real volume, and then you compare. And if this one is below this one, then you raise an alarm.
Okay, then the next question is, how long of the historical data you decided to using as the input data? How you decide that?
Yeah, so if you're not throwing events, it's actually to use less data. It's better to use less data. So 3 months is more than enough if you're not throwing any events. If you throw events, because the cycle of repetition of an event is very slow, could be a year, then you need to throw more data. So it depends. The events thing is really something that we're still working on, because I told you this, coming up with a good database all the time of events that's going to happen is really tough. So if you have the monitor at 3 months and you were able to come up with the false positives raised for an event, then you're good as well.
Okay, so it is designed by arbitration used, not by some scientific methods to measure how long? No, so if I understand correctly, 3 months of data without events is more than enough to estimate a good pattern, if you put the hinges right. Okay. And the final question is, do you do any normalization of the transaction volume to normalize into 0 to 1? No. No, okay. We don't do that. Thank you.
Okay, any other questions? Up the back.
Hi, thank you for the nice talk. Just one thing I'm not sure I've understood properly is whether you're raising alerts. Are you analyzing each time series in isolation, or are you doing some multivariate analysis? No, in isolation, purely in isolation. Okay. The only correlation we could see is macroeconomic things like events, right? That affects everyone, like Christmas. But you also see that in just one time series. So no, one in isolation. And you haven't, do you have any feedback on whether it would be interesting to do some correlation between them? Between the different time series you have? Whether, do you know if you are missing some relevant event that you could have tracked if you have done some multivariate analysis? We could, obviously. I don't know. This is how far we went to reach like production level tool. I'm sure you can do research on that, and especially for like same MCC, so same industry merchants on the same regions, you should see correlation with that, of course. For the pure purpose of detecting an anomaly on the fly, I think that the univariate data works fine. Okay, thanks.
Hi, thank you for the presentation. I have a question about using the UDF. Yeah. So if I understood well, you are grouping all the information of merchants on one row and then use any UDF. Did you face any limitation? For example, if you had, I don't know, time series data for more than 3 months for a year, were there any limitation on the computation?
It would be, of course. I mean, you can only squeeze that much, right? And the UDF, you know, you have your penalty because you're the serialization and so on. But for this use case, it just worked fine. I mean, it's also part of a learning curve. I mean, I was a bit like hesitant at the beginning, but it does work.
Okay, so for 3 months of data, and you had the.
We've trained a year. It's fine.
Okay.
Yeah.
And your data was it was univariate. Just.
Yeah.
Okay. Thank you.
Cheers.
Okay. Anyone else? Yep. I'll stop here on the way.
So you predict 1 week in advance, if I recall correctly. Oh,
yeah. Hi.
Hi. So does this mean you only have to train once a week?
Once a week is more than enough, to be honest. The data gets old, the predictions get old because of the trend components. So if you don't estimate well the trends, then you're going to be quickly off the, your seasonal component, you pick it up well. You can, so we try to predict, we in a 2 times per week training cycle, but it's more like a precaution measure. Yeah.
Okay, thanks.
Hi, thanks for the talk. I'm sorry if I missed that part, but how did you evaluate your model, or did you try and figure out what's the false positive rate and also the false negative rate? Because in this case, both matters.
So we use proxies to estimate precision and recall. The synthetic recall in outages on the test set, and then knowing if we are able to pick them up, and an outage being defined as what the people is eager to see and to pick up. And for the precision, we use just the alarm rate on the test set. It was work fine. The only thing you need to take into account is that you don't want a flat 0 there. So I mean, you need to allow for some noise because it's inherited. It's basically intrinsic to the model that you don't really have the truth estimate. And we're not keen on labeling this data neither.
Okay, a couple up the front.
Hey, I think it's a brilliant presentation. Thank you. I also use this profits model, and I wonder what's the major difference between the profits and the model that you.
No, very good. I love profit, but the problem is that we couldn't really just extract. We don't want to redo the whole scoring of profit in Java, right? So that's why. Yeah. And since we had to do that, we said, okay, we just adapt it. Model uses Fourier components, and we use Gaussian basis functions. And for us, it's better because you can. A natural frequency cannot estimate a thing like the distance to the last day of the month. So, for example, if you want, there's people that pay just the last day of the month. Now, it's not a 30 days natural cycle. There's months with 28 days, months with 31 days, right? So for us, this is better. The other thing is like a bit of ongoing work as well. Oh, the linear trend. Profit imposes a continuity condition on trends. And the other thing is the residual, the confidence intervals.
Sorry to disrupt you.
Yeah.
In the profit, that discontinuity, they set the several random points and to check which one is the best. So it is really hard to predict future. When it is a long term, how could you handle this uncertainty?
We're not
like long term forecasting.
Yeah, exactly. So the residual thingy. So the long term forecasting you can do again with the trend and the seasonal component. But what should happen is your confidence intervals grow because you become less confident on your prediction. Exactly. Again, this is ongoing work for us. So we haven't really we just have the solution for everything. So guys, don't work anymore in TimeSeries yourself. No, I mean it's still ongoing. Yeah.
Okay, great. Thank you.
Okay, we might leave it there. We're right on time. So once again, thank you, and please join me congratulating. Thank you once again.